Today I will talk on classical optimization technique, and that is the single variable optimization. Now, here we are dealing with the nonlinear programming problems. Now, as we know, optimization is an act of obtaining best result under the given circumstances. In any system, design, constructing, maintenance, everywhere decision maker has to take decision based on certain things, and decision mainly based on certain restrictions even. That is why the mathematical programming or optimization problems are with us to deal with the situation. Now, here we are dealing most general optimization problem, that is the nonlinear programming problem, which can be mathematically stated in this fashion. And here we are considering this is the general nonlinear programming problem, where n number of decision variables are involved, and we are having the constraints. The total number of constraints are m plus n number of constraints, and here we are trying to minimize f x subject to g I x lesser than equal to 0, where I is running from 1 to m, and h j x is also equal to 0, j is running 1 to n. Here we are having two kinds of constraints. Constraints are nothing but the restrictions which are imposed on us, and based on what we have to take the decision to maximize or minimize, or rather the optimize our objective function, that is f x. I will define what are these things. Before to that, just I want to mention that we have to, there are several alternatives in front of us. The alternatives are being confined with the restrictions given in the subject to conditions, and infinite number of alternatives. We have to select one out of that, so that our objective function is minimized in this case. Now, this is a general nonlinear programming problem, and our problem we have to solve. We have to select the values for x 1, x 2, x n that satisfy the restrictions and minimize the function f. Now, here the function f function is the objective function. Objective function is, we are setting the goal based on that. Based on that criteria, we are taking the decision. If it is effort, then we have to minimization of effort, that would be the goal for us, and if it is the benefit, then we always try to maximize the benefit. That is why objective function is as well named as the criterion function, and this objective function here, as I showed you, that this is nothing but a nonlinear function we have assumed, and this function is the function of n number of decision variables. Now, this function is nonlinear in nature. Not only that, the function g and h, these are all the nonlinear functions on Rn. That is why we are saying this kind of optimization problem as a nonlinear programming problem. Now, f is our objective function or the criterion function. Next is the set of vectors which satisfy all the inequality and equality constraints. This is called the feasible solution set of the problem, and feasible solution set only form the feasible space, and we have to select the optimal solution from the feasible space only, which will satisfy maximally our objective function, whether the objective function is minimization or maximization. Now, as I said, the collection of all such solutions form the feasible region, and the nonlinear programming problem is to find the feasible point among these feasible set, such that f x greater than equal to f x naught for all feasible point x. Here we have considered the minimization problem. That is why we are selecting x star in such a way from the feasible region that minimizes the function f. That is why f x star must be lesser than equal to for all other functional value at all feasible points. Then only we can say that x star is the optimal point for the said nonlinear programming problem. Now, the nonlinear programming problem can also be named as the mathematical programming problem, because this is nothing but the optimum seeking methodology, and this is being named as the optimization problem. This is being another, we are using the term, that is mathematical programming problem. Now, every mathematical programming problem can be categorized can be classified in different way. Classification can be done in different way due to the different kind of existence of constraints. It could be the nature of the decision variables. Now, here we are classifying the mathematical programming problem into two types. One type is the linear programming problem, which we have already talked about. Now, we are talking about the non-linear programming problem, where the function involved, objective function as well as the constraints, also these are non-linear in nature, and here we are dealing the non-linear programming problem in specific. Now, the optimization technique for solving the non-linear programming problem can also be categorized into two types. One is the analytic process. That's the analytic type, that's the process is the classical methodology, classical optimization technique. That's the today's topic for us, and this analytical classical technique is mainly based on the differential calculus method, and there is another numerical process is available with us. That is the non-classical optimization technique, that I will talk later on. One thing I should mention here, for linear programming problem we are having the simplex algorithm with us, and the simplex algorithm is something with one algorithm only we can solve every linear programming problem, but it is not so for the non-linear programming problem. Like linear programming problem, we do not have any single methodology to tackle non-linear programming problem, because non-linear programming problem generally complex in nature. Depending on the pattern of the functions involved, whether it is quadratic function, whether it is geometric functions, whether it is a fractional, depending on that there are different kinds of non-linear programming problem. Now, for every kind of problem there is its own methodology to tackle, but classical optimization technique is something which is based on the differential calculus method, and this differential calculus will help us in seeking optimal solution for nonlinear programming problem. Now, this classical optimization technique is based on the differential calculus method is in one hand, but in other hand it has certain limitations also, but I will come to that detail later on. But right now just I would like to mention that today we are dealing with the classical optimization technique. Non-classical or the numerical process will be different, and for different methodologies will be adopted for that. And this is the main thing for the classical technique. Since we are applying the differential calculus method, we are going for differential coefficients of the given functions. That is why one thing is important here, that the function which are involved in the mathematical programming problem, that functions must be not differentiable, that must be continuous, that must be, we should get the first order differential at least, we should get the other higher order differentials as well, otherwise classical optimization technique is not applicable. That is the limitation. That is why it is being mentioned here that it is not applicable for non-differentiable or not discontinuous functions. Now, coming to that, now there are also analytical method which is also depending on the differential calculus technique in locating the optimal solution, but here classical optimization techniques are being used for finding the optimal solution, that is the maximum solution or the minimum for continuous and differentiable functions which are involved in mathematical programming problem. Now, for finding out the optimal solution, the first step would be that problem formalization. Once the problem is being formulated, after that we need to find out the optimal solution. As I told you that the optimal solution is nothing but we have to select from the feasible region, and feasible region is having infinite number of points. That is why selecting optimal solution is not an easy task. There are certain conditions which had to be fulfilled, then only we can declare whatever decision we are taking, that is optimal. That is why we need to study the necessary and sufficient conditions for optimality for nonlinear programming problem. Now, this can be the necessary sufficient conditions. Again we will look for two kinds of nonlinear programming problems, two kind of mathematical programming problem. One is the unconstrained optimization problem and second one is the constraint optimization problem. And unconstrained optimization problem is something that will involve only the objective function and there is no restrictions on the given situation. That is why system is freely movable, and in that case we are dealing two kinds of unconstrained optimization problem. One is the single variable optimization problem and another one is the multivariable optimization problem where we do not have any constraint. That is why this is unconstrained. And for the constraint optimization problem, we will deal with two kinds of situation. One is the multivariate function with both inequality and equality sign, and another one multivariate function with both equality and inequality constraints. A more general form is being mentioned here. That is why we will look for necessary and sufficient conditions for locating optimal solution for unconstrained optimization and constraint optimization problems. Today I am dealing with the single variable unconstrained optimization problem, and we will learn the classical optimization technique to find out the optimal solution for it. This is a nonlinear function for us. X is the decision variable domain and f(x) is the function given for us, and this is the objective function. We need to maximize or minimize this objective function. If we just analyze the function in the domain of x, if we just partition the domain, then what we will see in some portion of the interval, in the subintervals functions, our pattern is changing. In one part there is a, in the first part if we see that there is a maximum point. In the second part we are having a minimum point. That is why there is a concept in the nonlinear programming problem. We not only go for the minimization or the maximum or minimum point, also we are trying to find out the local or the global maxima or the local or the global minima. These are different in meaning. If we just see that globally in the third interval, in the third subinterval we are having the global maximum, but if we see we are having one local maximum in the first subinterval rather. That is why the concept, as I said, formally I will tell you mathematically how to define local maxima, local minima, rather the relative maxima, relative minima, or the global maxima or the global minima. That is why in the third interval we are having the global maximum and we are having the global minimum in the fourth interval. That is why our task would be to find out the relative or the local minima or maxima or the global minima or maxima for the single variable optimization problem. Now, single variable optimization problem. Identification of optimal point is our primary concern. That is why let us consider f(x), a function that is continuous function defined in certain interval a b in the real line, and we have to select the decision that x star which will maximize or minimize the function f(x). That is our objective for today's lecture. Now, we are defining mathematically what is the meaning of the local minima. As I said, function is defined over the whole interval a to b, but function is changing its pattern in between. That is why function is non-linear in nature. That is why in some portion we will get the local minima, and the local minima can be defined in this way. A function of one variable, function f(x) is said to have a relative or the local minimum at the point x equal to x star if f(x) star lesser than equal to f(x) star plus h, where for all sufficiently small positive and negative values for h, we are taking a small neighborhood of x star in the domain, and we see everywhere in that small neighborhood f(x) star is the minimum value. That is why we are declaring x star is the corresponding relative or local minima for the given function f(x). Similarly, we can define relative or the local maximum. We can say x star is the point, that is the relative maximum for us. If we consider a neighborhood of x star in the real line, That is why for all sufficiently small positive and negative values for h, if we can establish that f x star is greater than equal to f x star plus h, then we can declare x star is the relative or the local maximum for the given function f x. Here we need to see that function f x is only the function of one variable, function of only one variable, that is x. That is why in this way we can define the local or global, local or the local minima, local maxima. Similarly, we can define the global minimum or the absolute minimum as well. A function of one variable f x is said to have a global or absolute minimum at x equal to x star if f x star lesser than equal to f x for all x belonging to the given domain of definition, that is a to b, that is the interval, whole interval. If we get at least one point, that x star, then we can declare the corresponding point would be the global minimum, where the condition f x star is lesser than equal to f x for all x within a to b. Similarly, we can define global maximum. We can say function f x will have a global or absolute maximum at x equal to x star if f x star greater than equal to f x for all x in between a to b. That is the definition for us. Now, how to find out the global or local minima or maxima, that is our concern in the next. In continuation to it, I would say that the point x star will be defined as a stationary point if the function has either maximum or minimum. But sometimes it happens that function may not be at certain point, point is stationary. How to check the stationary point, that I will tell you in the next, but we can see that some points are stationary where the maximum or the minimum will occur, but that is not the maximum minima. That point is being named as the point of inflection, that will be defined later on with the graph, but just here I would like to mention that there can also have certain points of inflection within the given domain. Now, at the maximum point, the function changes from increasing to decreasing pattern, and at the minimum point function changes its pattern from decreasing to increasing, but at the point of inflection, on the either side of the point of inflection, we will see either the function is increasing or on either side of the point of the inflection the function is decreasing. Now, that is the graphical meaning of the point of inflection, but mathematically how to detect, just we have to go for the differential calculus method. We will go for the differential differentials for it, that is a first order differential, second order differential, and we will decide accordingly. But if you look at the curve, just see, there is a global minima in the first, in the next there is a point of inflection, and as we see that at the minimum or the maximum point, if we just take the tangent at the point, that will be parallel to x axis. That is the general idea we know in mathematics, that at the point of maxima or minima the tangent is parallel to x axis. But if we see the graph again, we will see at the point of inflection as well the tangent is parallel to x axis, but that is not a maxima, that is not a minimum, because in this case function is increasing in either side of the inflection point. But if we see at the maximum point, the function is increasing in the left hand side and decreasing in the right hand side. Similarly, for the local or global minima, the function is decreasing in the left hand side and increasing in the right hand side. This way we can select the stationary points for a given function of single variable in the next. And this is the formal definition of single variable optimization problem. A single variable optimization problem is the mathematical programming problem in which only one variable is involved and the value x equal to x star is to be found in the interval a to b, which minimizes the function f x. For example, we can determine the maximum and the minimum value of the function f x equal to 3x to the power 4 minus 4x cube minus 24x square plus 48x plus 15. As we see, this function is nonlinear in nature, it involves only one decision variable, that is x. Now, our task is to find out maximum or the minimum value of this function, rather the optimal points, rather the stationary points for this function. For dealing that, we need to learn the necessary condition for the problem. The necessary condition tells us that if a function f x is defined in the interval a to b and has a stationary point, that is relative minimum or maximum or the point of inflection at x equal to x star, where x star is also a member from a to b, then the first order derivative of f x at that point x equal to x star would be is equal to 0. That is why it has been said that d of f x by dx, that is equal to f dot x, that exists and it has a finite number, and at every point and at x equal to x star the value is equal to 0. That is a necessary condition to identify stationary point of a given nonlinear function. Now, we need to prove that whether at the relative minimum or the relative maximum or the point of inflection, the first order derivative equal to 0. Let us try to see what is the definition of the first order derivative at that point. According to the definition, f dot x star must be is equal to limit h tends to 0, f of x star plus h minus f x star divided by h. And we need to prove that f dot x star is equal to 0, and we have assumed that x star is the point or relative minimum. Now, if it is relative minimum, then by definition, if I consider the neighborhood of x star, small neighborhood where h is very small, that means h could be negative, h could be positive. If we just take the functional value at different points, then this relationship holds that f x star is lesser than equal to f x star plus h for relative minimum, and that is why we can say that f x star plus h minus f x star greater than 0 when all of this is 0 always, f x star plus h minus f x star greater than equal to 0 for every point within that neighborhood. But if I consider h greater than 0, then this ratio f x star plus h minus f x star divided by h is greater than equal to 0 for h greater than 0, and f x star plus h minus f x star divided by h lesser than equal to 0 for h less than 0. But as we have assumed that it cannot happen, we have assumed that limit value must exist. That is why left hand limit must coincide with the right hand limit, and it should coincide with the limit at that point. That is why the only possibility is that f dot x star must be is equal to 0. If we consider the limiting value h tending to 0 from the left hand side as well as from the right hand side. That is why like this we can prove that for relative minimum, that first order partial derivative of f at x star would be is equal to 0. Similarly, we can prove for the relative maximum as well. In that case, only consideration would be that in the neighborhood of x star, f x star is greater than equal to f x star plus h, and the rest of the logic will remain as it is. Only the when we are considering the ratios, that will just reverse, it will be f x star plus h minus f x star divided by h, it would be lesser than equal to 0 for h greater than 0, and in the next the reverse case greater than equal to 0 when h lesser than 0. And as we assume that the limit value exists finitely, that is why the only possibility is that it must coincide with both the values must coincide, and the only thing is that f dot x star is equal to 0. That is why we can conclude from the necessary condition that for the relative maxima or the relative minima, the relative maxima, the first order partial derivative at that point it is equal to 0. Now, similar thing will happen for the at the point of inflection as well. This is also equal to 0 since f dot, that since the function is changing its pattern, it is going from concavity to convexity or convexity to concavity, at the point of inflection is changing its sign, that is why the f dot x is 0 at that point. And this is only the necessary condition for finding out the optimal point. But from here there are certain limitations. What are the limitations? The necessary condition does not tell us what will happen if the maxima or the minima point occur at the end points, or what will happen if the function is there is a there is a kink in between, and then or at the point of inflection also what will happen, nothing has been said in this case. That is why we are going for the next level condition, through which we are trying to ensure whatever stationary points we have achieved from the necessary points, these are also the sufficient conditions have been proved to ensure that these are also the relative maxima or the minima. That is why in the next we are going for the sufficient condition for the continuous functions, and this is the thing we are now going to tell you. Now, this is the sufficient condition for optimality for function of single variable. Now, if x star is the optimal point, and if we see the function is differentiable further, then up to n minus 1th order derivative, if we see the function at the optimal point is all at 0, but nth order derivative is not equal to 0, then sufficient condition tells us that x equal to x star would be the local minimum value of f x if f n x star is greater than 0 when n is even, and it would be local maximum value of f x if f n x star is lesser than 0 and n is even. But when n is odd, we cannot say anything about the nature of the extreme point. We will say it is neither maximum nor minimum, that is the saddle point rather. That is why this point is being said as the point of inflection. Now, this is the sufficient condition and we want to prove this condition. Again we are applying the Taylor series here, and we are considering Taylor series with Lagrange form of remainder, that f x star plus h f x star plus h into f dot x star h square by factorial to f double dot x star up to n minus 1th order it is there, and nth order is h n by n factorial f n x star plus theta h. And in the we have assumed that up to n minus 1th order the functional derivative vanish. That is why all the terms starting from the second term will all vanish, only the last term will remain. That is why the optimal point x star point is whether maxima or minima, that totally depends on the sign of f x star plus h minus f x star. That is why if this is the expression for us, it is very clear that f x star plus h minus f x star is totally dependent on the sign of h to the power n by n factorial f n x star plus theta h. Thus, we can say that f n x star plus h minus f x star would be is equal to this. Now, if we consider n is even, then for every h, h to the power n by n factorial is positive. That is why the term f x star plus h minus f x star, this is totally dependent on the sign of this is totally dependent on the sign of f n x star, and it is dependent on f n x star plus theta h. Now, we are saying that f x star plus h minus f x star has the same sign with f n x star because we have assumed that x star is the extreme point of the given optimization problem. If x star is the extreme point, then in the neighborhood of x star, f n x star is having the same sign. That is why the sign of f n x star plus theta h, this is same as the sign of f n x star. Thus, we can conclude that f n x star plus h minus f x star has same sign with f n x star when n is even, and certainly when n is even, from the given condition we can say that f x star minus f x is positive if f n x star is positive, and f x star plus h minus f x star will be positive, then the corresponding x star would be the relative minimum for us. And similarly, if f n x star is negative, that is f n x star plus h minus f x star, if it is negative, then we will get the corresponding relative maximum value. That is why when n is even, from the previous expression we can conclude that if the nth, looking at the sign of the nth derivative, we can see it. But when n is odd, then we cannot say anything about the sign of h to the power n by n factorial. That is why depending on different value of h, depending on the sign of h, depending on the value of n, the f x star plus h minus f x star will change. There is no pattern, it won't follow any pattern. That is why when n is odd, we cannot say whether x star is maxima or minima. Thus our sufficient condition follows that if n is odd, if we see that up to n minus 1th order functional derivative at the extreme point order coming 0, then we will consider as the corresponding point is relative minima if f n x star is positive, and relative maxima if f n x star is negative. And if n is odd, then nothing can be said about this. Let us consider this optimization problem. We want to find out that maximum and minimum values of this function, where the function is of order 4, 3x to the power 4 minus 4x cube minus 24x square plus 48x plus 15. If we just we have to go further, we have to find out the stationary points for this function. For finding out the stationary point, necessary condition tells us that we have to equate the first order derivative to 0. Then we will get the stationary point x equal to 1, x equal to 2, x equal to minus 2. If we look at the graph here through the graph, it gives us certain idea that x equal to minus 2, there is a possible minima is there. At x equal to plus 2, there is possible maxima as well at possible minima, and x equal to plus 1, there is a possible maxima. These are all the local maxima minima I am talking about. Nothing can be said about the global optimality here. Now, that is why first order derivative tells us that the possible extreme points are x equal to 1, x equal to 2 and x equal to minus 2. For checking whether x equal to 1, x equal to 2, x equal to minus 2, these are all the minima, relative or relative maxima, we need to calculate the second order derivative. The second order derivative, the value is 36 x square minus 24 x minus 48. Again, if we see at x equal to 1, the second order derivative is negative. That is why we can say that x equal to 1, that function is having local maxima. Look at the graph, it is giving the same impression to us. If we go for a second order derivative of function at x equal to 2, it is positive. At x equal to 0 also it is positive. That is why we can conclude that x equal to 0 and x equal to 2, these are all the relative minima for us, and these have been summarized here with the corresponding functional values. Now, one thing it is clear here that whatever we have said, this only we have said about the local optimality. We have said where the function is having relative or local maxima, relative or local minima. We could not say anything about the global optimality. That study is very much needed in the next. Now, let us take another problem where the function is of order 6. Now, 2x to the power 6 minus 6x to the power 4 plus 6x square plus 10, and this is the function for us, this is the graph for us. Again the same, we need to find out where the function is having the maxima or the function is having the minima. It is very clear that from the graph at the point 0, x equal to 0, function is having a relative minima point, rather within the range, given range, that is from minus 1.5 to plus 1.5, the corresponding minima is again the global minima as well, but we will not study that one. We will see the first, we will see the stationary points, possible extreme, possible optimal points. For that thing again we will apply the necessary condition, and necessary condition we will tells us that we will just take the first order derivative of the function, we will equate to 0, and we are getting the necessary points at 0 plus minus 1. But plus minus 1 at those points from the graph, it is clear that function cannot have any maxima or minima. That is why we are expecting from the graph in the second order derivative must tell us that function is having point of inflection at these 2 points plus minus 1, and at point 0 function is having the relative minima point. For confirming that conclusion, we are looking at the graph will not be sufficient for us. That is why we are going for the second order derivative, and second order derivative tells us that at x equal to 0 f double dot x is positive, then certainly at x equal to 0 that is relative minima for us. Now, what about x equal to plus minus 1? We see that second order derivative functional derivative is equal to 0. That is why we need further study. We can't say anything again here. We will go for the third order derivative. In the third order derivative, what we see? We see that at x equal to 1, the third order derivative is positive, at x equal to minus 1, third order derivative is negative. Thus, we see again the order of the derivative is not even, that is odd. That is why, as we know that if the order of the derivative is coming non-zero value, then we can't conclude anything about that. Or if it is even, then only we can conclude about the extreme value, extreme points, whether maxima or minima. Thus, we can say that x equal to 1 and x equal to minus 1, the function is having the points of inflection. Now, the whatever classical optimization techniques we have learned the necessary and sufficient condition, these are only applicable where the function is differentiable and the function is continuous. But there are certain limitations as well. If the theorem does not say anything about where the minimum or maximum occur at a point, but the derivative fails to exist. That is why this is one of the limitation. The next limitation is that if the function is defined within a bound within an interval, what is happening at the end points? There can have also the extreme point. That is why at these two cases the classical optimization technique fails to say anything. We need further technique to handle those situations. For explaining further these limitations, let us take certain example for it. This is a function for us. This is x, this is f x, and the function is defined within a to b, and this is the pattern of the function. This point is a and here the point is b. In between there is a point x naught point, and it is very clear that at point x naught the function is not differentiable. Thus, x naught is not an extreme point. Again, if we consider another function in the similar fashion, where this is b for us, function is defined from a to b, and this is the point x naught again, x naught at x naught, the first order derivative fails, again x naught is not an extreme point. But if I consider the other example, where the first order derivative fails, but still we can't say this is not an extreme point. This is the function for us defined from a to b, and this is the point x naught point. As we see the graph, at point x naught function is having a local minima, but first order derivative fails here. The necessary condition cannot help us to say anything about x naught, but still x naught is local minima. Similarly, let us consider another situation. The function is defined from a to b, a is the point, b is another point, and x naught is a point in between, where x naught is having the local maxima, but again the first order derivative fails here. Thus, if the first order derivative fails, then what will happen about the optimality? It is not the classical optimization technique cannot help us, but still if we have to take a decision if the situation is such that the objective function is like this. That is why we should have certain technique through which we can say something about this, and that is needed for further, we should have further study on this. Let us take this next case, next limitation. This is our x and this is the this is f x, and the function is defined like this from a to b. what we see at point A, f dot A, is it 0? Not really, f dot A is greater than 0, but we have to say A is local minima, rather x equal to A is local minima. Still we are having f dot A is greater than 0. Similarly, if the function is like this, similarly at point B, the same case at the end point, if the function is this one, at point B from A to B, at point B f dot B is lesser than 0, because the function is decreasing. And in this case, if we apply the classical optimization technique, we can't say anything about x equal to B. We will say B is not an extreme point, but this is not so, because looking at the graph, it is very clear that B is a x equal to B is a local minima. Similarly, if we just draw other graphs as well, at point A B as well, at point A there is a local minima, at point B there is a local maxima. That is why these are the things we need further study, where first order derivative is fails, the other necessary condition cannot provide us the extreme point. That is the limitation has been said in this way. And not only that, I should mention here as well, whatever classical optimization we have learned till now, we did not say anything about the global optimality. That is why global optimality is another topic we need to study further. And in this connection, let us take one of this is a very interesting function, and let us see what is happening for this function. The function is defined in this way: 2 minus x minus 1 whole square. If x is in between 0 to 3, it excludes the point 3, and this is minus 3 plus x minus 4 whole square if x starts from 3 including 3 to 6. All right. Now, if it is and we need to maximize this function, this is unconstant optimization. Again, we need to maximize this function. If I draw the graph for this, we will see the graph would be like this: 0, 1, 2, 3, 4, 1, 2, 3, 4, 5, 6. Function is defined up to 6, and if I just draw it, function will be like this. At 1 it will be maxima, then again it will come down. At 4 it will be local minima, and this is defined up to this. This is the graph for us. Now, we need to apply without looking at the graph, let us try to apply the classical optimization technique. For applying classical optimization technique, we need to have the first order partial derivative. We are having the first order derivative, it is not the partial derivative. This is the derivative, single variable, 2 into x minus 1 if x is in between 0 to 3 excluding 3, and it would be 2 into x minus 4 if it is 3 to 6, which includes the point 3. And if we go for the second order derivative f dot x, because first order derivative we will get the necessary condition, second order derivative tells us about the sufficient condition. This would be is equal to minus 2 and this would be is equal to 2, x lesser than 3, 3, x less than c. Now, let us see what is happening for the points x equal to 0, x equal to 1, x equal to 3, x equal to 4 and x equal to 6. Let us first try x equal to 1. At x equal to 1, f dot x would be is equal to 0, certainly. F double dot x would be is equal to x equal to 1, it should be minus 2. Then what is the conclusion? This is the local maximum point. X equal to 1 is the local maxima for us. Now, what about x equal to 4? X equal to 4, f dot x is 0, and f double dot x equal to 4, it would be 2. This is greater than 0, positive. That is why x equal to 4 is the local minimum point. Thus, if we just equate f dot x equal to 0, only we are getting 2 points, x equal to 1 and x equal to 4. Thus, using the classical optimization technique, we can conclude for this function we are only having 2 extreme points. One is the local maxima, another one is the local minima. Local maxima at x equal to 1, certainly graph tells us the same, and x equal to 4, the function is having the local minima. But if we look at the graph at the end points at x equal to 0, at x equal to 6, the function is having local minima and the local maxima. Thus, it is not that we can't say anything about that, and x equal to 3 is a point in between, because at point 3 the functional pattern changes. And the part is that, the thing is that if we analyze the function further without looking at the graph, at x equal to 3, f dot x does not exist, because the first order derivative value at x equal to 3 are different. This is the thing. And for x equal to 0, what we see at x equal to 0, f dot 0 is greater than, is equal to 2, 2 greater than 0. That is the classical optimization technique tells that x equal to 0 is not a possible extreme point, the necessary condition tells us, but it is very clear that 0 is the, x equal to 0 is the local minimum point for us. Similarly, for the x equal to 6, what we see, f dot 6 is equal to 6 minus 4, that is 2, 2 into 2 it is 4, that is greater than 0. Again classical optimization technique tells us that at the end points at x equal to 6, the function cannot have any local maxima or local minima, but it is very clear that we are having local maxima here. Thus, if we apply straight away the classical optimization technique, we only can conclude for x equal to 1 and x equal to 4, nothing we can say further. But if I want to analyze the function in a, better way, it is better to analyze in a, we should view the function in a different angle. Thus, whether the first order partial derivative is greater than 0 or less than 0 or does not exist, that also should be considered. Thus, we say more about this x equal to 0, x equal to 3 and x equal to 6, and thus the classical optimization technique is not applicable everywhere, and we should have some process, numerical process to handle this kind of situation, so that we need not to ignore the points x equal to 0, x equal to 3 and x equal to 6. That should be the further, that will be detailed in the next, and thus we are concluding today's lecture with the conclusion that we are determining the maximum and minimum points of an unconstrained optimization problem using a classical optimization technique, which involves single variable where the objective function is continuous and differentiable, and we only dealt with the necessary and sufficient conditions for this, and this is the reference for us. Author is Hamdiye Taha. The next is this is a very important book, Engineering Optimization Theory and Practice, by the author S.S. Rao, and the other one is the Quantitative Techniques in Management by N.D. Vora, that is McGraw-Hill publication. Thank you for today.